So about half of my group's research revolves around trying to understand how the Earth's environment has evolved over time, especially over deep time, over billions of years of Earth history. We do a lot of work developing new techniques to determine how much oxygen was in the oceans in the distant past. That relates to how much oxygen was in the atmosphere in the distant past. We want to reconstruct how the Earth transformed from being a planet that had almost no oxygen, no molecular oxygen, O2, at its surface, to being the world we know today, which has 21% oxygen in the atmosphere, which enables life like us to exist. That transition happened about halfway through Earth history, about 2.5 billion years ago. We still at this time don't really know exactly why that happened. So what we do is we make painstaking chemical measurements, measuring trace metal abundances and the isotope compositions of trace metals in ancient sedimentary rocks laid down in ancient oceans. And from the abundances of different metals and changes in their isotope abundances, we can reconstruct what the oxygen levels were in the environment at the time. Some organisms require oxygen, like you and me. Some organisms produce oxygen, whether they're plants or cyanobacteria. And then for many organisms, oxygen is toxic. Oxygen is a very reactive molecule. You and I can exist in this oxygenated environment because we've developed very complicated molecular mechanisms to cope with oxidative damage. So the history of life and the evolution of life, to a large extent, is a battle, right, between those microbes that learned how to produce oxygen, which created a terrible catastrophe for the pre-existing ecosystem that was adapted and happy and dependent on a low oxygen environment. And so understanding that interplay and how that has shaped the course of evolution is powerfully important.